In everyday life, we continually face the need of estimating such physical quantities as length, mass, time, temperature, electrical and magnetic quantities, quality parameters of products, and so on. So in this lesson, we will talk about various physical quantities and its estimation and strategies for including vectors. Measurements are everywhere, and we can use different measuring tools to quantify things around us. Just think, for example, of the GPS. We have lots of satellites outside the Earth, and these satellites help us to give information about a specific location here in our planet using our mobile phones. So, in this process, it simply requires measurement. Measurement helps us to make decisions when to visit doctors, to look for our health, be guided by different technologies in measuring what we need, to go through a specific location via transportations, helps us to tell weather, and know the proper consumption of energy. For measurements to have meaning, they must use common units.
Let's define what a measurement is and what it actually means to measure something. Well, in science, a measurement is considered the assignment of a numerical value to a physical quantity with a certain basic arbitrarily chosen, internationally accepted reference standard code unit. Measuring of physical properties such as length, volume, and density is very common. For example, you might want to know the length of a line, the volume of a sphere, or a density of a liquid.
Whenever we take measurements, we also have to assign units to the numerical quantity in order to convey the relative size or magnitude of property in question. For instance, if I said the length of my shoe is 9, you wouldn't actually know how long my shoe was, because there's no context for what the 9 represents. In fact, these measures would only make sense if the number 9 have a unit of measure to go along with it. Makes sense, right?
Notice that in our chart, the highlighted is our base units. It actually helps to define more complex units or combinations of base units. These obtained derived quantities are called derived units. For example, area is a physical property that uses a unit called meter squared. Since meter squared requires the meter in order to be defined, it is considered a derived measure or unit. Let's walk through an example that will illustrate how the meter is actually used to define an area in meters squared. If we take a line that is 2 meters in length and then create a square from 4 of these same lines, we can find out the area of two-dimensional space that this square occupies by squaring the length of the original line. We'll not focus on mathematical concepts of squaring, but know that, in essence, we're multiplying base length measurement by another base length measurement.
In earlier time, scientists of different countries were using different systems of base units for length, mass, and time for measurement. 3 such systems were, first, the CGS system or centimeter, gram, and second respectively. Second, we have the FPS system or foot, pound, and second respectively. And last, we have the MKS system or meter, kilogram, and second respectively. In the 1960 International System of Units, abbreviated SI, is the modern form of the metric system. It is the system of units that the General Conference on Weights and Measures has agreed upon, and is legally enforced in almost all parts of the world. This table shows the SI-based quantities and its symbols and definitions. This table, on the other hand, presents some of the retained units outside International System of Units.
A short recap of the scientific notation, which is conveniently and widely used in expressing large and small numbers. We have the form of the uppercase letter N times 10 raised to lowercase letter n, where uppercase letter n is greater than or equal to 1 but less than 10, and lowercase letter n is the appropriate power of 10. Expressing this value into scientific notation, we obtained 3 times 10 raised to 8 meters per second. Second, the mass of a strand of hair is approximately 62 millionth of a kilogram. Expressing this value into scientific notation, we obtained 6.2 times 10 raised to negative 7 kilograms. This table shows different SI prefixes that can be used in presenting measurements. Conversion is a multi-step process that involves multiplication or division by a numerical factor, selection of the correct number of significant digits, and rounding. Now, to convert unit to another, its simplest way is to use a conversion ratio with the desired unit on the numerator and the unit to be converted at the denominator. For example, express the following quantities in the units requested. Express your answer in scientific notation. During your chemistry laboratory class, your beaker contains 578 milliliters of water, but as per instructions on your laboratory manual, volume should be in quarts. What is its volume in quarts? Note that we are converting metric unit of volume into an English unit of volume. Kindly refer to the table of conversion that is uploaded in your Google Classroom. And to solve this problem using conversion ratio, we have 578 milliliters times 1 liter is to 1000 milliliter times 1 quart is to 9500th of a liter. Performing the indicated operation, we obtained 60,842,105,263 trillion of a quart, or 6 and 800 times 10 to the negative 1 quart. Thus, the beaker with 578 milliliter of water has a volume of 6 and 800 times 10 to the negative 1 in quarts. Another example, if the density of an object is 2 and 8700 times 10 to the negative 4 pounds in cubic inches, what is its density in gram per milliliter? To solve this problem, we have 2 and 8700 times 10 to the negative 4 pounds in cubic inches times 1 pound is to 454 grams times 1 inches cube is to 2 and 5400 centimeter cube times 1 cubic centimeter is to 1 milliliter, and performing the indicated operation, we obtained 79,512,781 billionth of gram per milliliter, or 7 and 9500 times 10 to the negative 3 gram per milliliter. Thus, the density of an object that is 2 and 8700 times 10 to the negative 4 pounds cubic inches in gram per milliliter is 7 and 96th times 10 to the negative 3 gram per milliliter.
Moving on to our next topic. If an object moves in a straight line, we can describe its motion by describing how far or how fast it moves, or whether it moves to the left or to the right of the origin. But when we look at the motion of an object that is moving in 2 or 3 dimensions, we need more than just plus and minus signs to indicate direction.
Quantities with magnitude but no associated direction, such as speed, mass, volume, and time, are called scalars. For example, the motorcycle time to travel its destination, the volume of its gas tank, the combined mass of the rider and motorcycle, the temperature of motorcycle battery, and the distance traveled by the motorcycle. Moreover, quantities that have magnitude and direction, such as velocity, acceleration, and force, are called vectors. For example, the velocity and acceleration of a motorcycle, the momentum of the motorcycle to have the same amount of momentum as the cement truck, the external force that pushes on the motorcycle in the direction of the center of the circle when it takes turn, and the weight of the motorcycle or the rider.
An arrow is a convenient way to draw a vector since both length and direction are indicated. A real number is the best way to represent scalar, which, when multiplied by a vector, changes its length. The symbol for vector quantity is an italicized capital letter in boldface or a letter with an arrow on top. And now for a short trivia. Did you know that the English word vector came from the Latin word vectus, which means to carry? And now we have here a mosquito. A mosquito is considered to be a vector because a mosquito is a disease-carrying organism.
The direction of a vector is the acute angle it makes with the east-west line. The word north or south is written after the measure of the angle followed by the phrase of east or of west. For example, specify the direction of vectors A, B, C, and D. For vector A, we have 50 degrees north of east. For vector B, we have northwest. For vector C, we have 20 degrees south of east. In vector D, we have south. Note that whenever the vector has an angle of 45 degrees, you can write it without including the angle. That is vector B. A variety of mathematical operations may be performed on vectors. While scalar quantities obey the ordinary rules of arithmetic in addition, subtraction, multiplication, and division, vector quantities are treated in a different way. The directions must be taken into consideration. One of the important definitions under vector addition is the resultant vector, or simply resultant, and it refers to the sum of two or more vector quantities and is denoted by uppercase letter R. To illustrate resultant vector, we have vector 1 plus vector 2 plus vector 3 is equal to resultant. There are two important properties of vector addition. First, vector addition is commutative. That is, the order of adding vectors may be changed without affecting the resultant. In symbols, A plus B is equal to B plus A. To illustrate the commutativity of vectors, we have vector A plus vector B is equal to resultant, while vector B plus vector A is equal to resultant. Note that the magnitude and direction of the resultant are just the same. Therefore, resultant is commutative. Next, vector addition is also associative. That is, the grouping of vectors to be added may also be changed without affecting the resultant. In symbols, the sum of A plus B plus C is equal to A plus the sum of B plus C. To illustrate the associativity of vectors, we have A plus B plus C is equal to resultant, and B plus C plus A is equal to resultant. Note that the magnitude and the resultant of both illustrations are the same.
Thank you very much for watching. We hope that you learned. See you on our next topic. Bye!